machine, the A machine is actually equivalent to this. So again, let's start from toy example. Which actually is absolutely classical and provides something very interesting in the way I define it. So suppose we have a finite group G. It's a good point for example. So this is a finite group. And we have a subgroup. Then, well, there's multiplication of the group. But somehow we want to, yeah, so K acts on G from the left and from the right. Yeah, yes. That's what I was thinking about, yes.
The whole thing is kind of quantum. You make sure your previous video is there. Yeah. But it's too much uncertainty. You can either have a position or a moment. Sorry.
I'm just trying to decorate the picture, not adding anything, waiting for others to come. So let me repeat. So we're discussing the way to produce algebra representation theory from geometry, and yesterday was one example of this. Today will be another example. The general approach is to first construct everything geometrically so that it will be clear how maps go, what diagrams commute, and so on. So to have the associativity and other things built in, and then just to apply some algebraic machine which produces from this geometric or topological picture the actual picture with the representations. And the bonus is that to the same geometric picture we can apply different algebraic machines, and then every time we get some result. Of course, depending on the type of machine we're applying, the answers will be different, but at least all relations will be automatically satisfied algebraically because they are already satisfied geometrically. So here is a toy example, and now everything is discrete. There's no geometry, it's just set theory. So we have a finite group and a subgroup, and we have left and right translation actions. So there'll be other examples further. And so what we can do, we can consider, well, let me call this vector space F. These are just functions, say complex valued functions on the group G, which are invariant under translations both from the left and from the right. So this is the same as functions on, so this is called bi-invariant functions, and this is the same as functions on double cosets. So then again, this is not, anything fancy. It's not a stack or anything. It's just a set right now. Okay, so then we have multiplication on G. Now we want to take into account K as well. So we just write this picture. So these are sets, as I said. Now there's a map like this from G times G, left quotient by K, right quotient by K, and also diagonal quotient by K. So here we take quotient from each side. Here we take quotient by the diagonal action. Now notice that multiplication in the group, this map M. So let me denote this map by delta. And multiplication map M factors through this quotient because maybe I should not call this diagonal. Well, I won't use it ever. So it was just an example. But this is the diagonal action. So it multiplies from the right by K inverse and from the left by K. So if we take the product, these two cancel each other. So the map M is defined like this. Then you can start from functions here. So functions here, these are sets. So functions here is just f tensor f, right? Because it's the product. So this is just a vector space with bases given by elements here. So this is tensor product. Now we can pull back a function and get here. And then we can, again, like yesterday, we can push forward. We can integrate. So this is summation over the fibers of the map. So F becomes, so let's denote this total operation by star. So we have so this star is called convolution, and we have convolution operation like this. And a very easy exercise tells us that F with convolution is an associative algebra.
You mean across?
Huh?
I didn't say across. It's across of. No. This is F is functions.
F is functions on each of these. So functions on the product are tensor product. It's tensor product. Basis here is given by the product, right? So is an associative algebra. So let me give an example of example. G is GLN over some finite field FQ. And let's take B in, K. K is the standard Borel, just upper triangular matrices. So from now on, I'm skipping the notation K. I just used it here, not to specify them that I'm actually.
Is this a multiplication restricted to K binary functions?
No, it's just taking quotient by more action. So
K binary functions are not don't
So any function which is no, right now I'm talking about sets, right? So any coset like this can be taken quotient of, and you get a coset like this. In other words, any function which is k times k invariant here, after lifting, becomes a function which is just k delta invariant. It's restriction of invariance. Okay, so in this case, this f. So first of all, what is the double coset? So this is in bijection with the symmetric group of order n. It's always like this. Double cosets for upper triangular matrices are enumerated by permutations. So we get a vector space F, which has the size of the symmetric group, and it's an algebra. However, canonically is not the group algebra of the symmetric group as one could expect, but is the what is known as Hecke algebra. So in this case, generators are Ti, I equals 1 to n, and relations are well, the standard braid relations. And then, well, Ti, Tj commute. If they're far away. And finally, well, I hope I'm not making a mistake. There could be a mistake with the parameter, but I hope not. So the final relation, instead of Ti squared equal to 0, we have Ti minus q, Ti plus 1 equals to 0. So this is the Hecke algebra relation. And again, I could make a mistake here. So I didn't check that the parameter is exactly the order of the finite field. It should be, but maybe it's q squared, in fact. So anyways, by rescaling, I mean, after all, this is just a number. So by rescaling, you can identify this algebra over complex numbers with the group algebra of the symmetric group. But you need some rescaling. Okay, so this was a toy example, and again, the message was that we start from some geometric picture, we apply some elementary algebraic machinery, which in this case is taking functions on the set, and we get some algebra which proves to be interesting even in the simplest cases. So now let's discuss the actual construction, and in the construction there will be categories instead of vector spaces. So given, so my machine, my algebraic machine applied to geometry will produce as an outcome not a vector space like this F, but a category. And the convolution will be a monoidal structure on this category instead of associative product. So let me fix notations. So from now on, G is a simple algebraic group. and if you wish, it's always SLN over complex numbers. So from now on, we work over complex numbers only. Now B is the standard. So we fix. So this is the maximal torus. This is the Borel, chosen Borel subgroup, and then I have corresponding Lie algebras. And just like yesterday, in the SLN case, B consists of upper triangular matrices and T consists of just diagonal matrices. Well, in SLN, so determinant equals to 1. Also, I'll need the minimal parabolic subgroups. So they are enumerated by simple roots. And you should think about the picture with SLN. So in the SLN case, Pi consists of matrices which look like this. So they have determinant 1, of course, and also they're almost everywhere upper triangular. And only in the i's place, we allow one small corner under the diagonal. Okay, so now we are doing both representation theory and algebraic geometry. So for us, an algebraic group, whatever group we take, K is the same as the algebra of functions. On K, and then since we have the product K times K to K, so it's the multiplication in the group, then pulling back functions produces a map from OK to OK times K, which is the same as OK tensor OK. So it's a coproduct, and it's a Hopf algebra structure. So, of course, you have counit, so you can take any function and restrict it to 1. You'll get a number. So, I mean, calculate its value at the unit element in the group. You'll get a number. So you have co-multiplication to the base field, which is C. So this is a, well, I'll need only the co-algebra structure in all this. So definition, which is equivalent to all other definitions of representations, the category of representations of K in algebraic sense is just OK, which is a co-algebra, comodules. So if you think about it, the usual notion of representation provides such structure. So imagine we have a representation K times V to V, right? Then applying functions, you'll get OK tensor sim V star to sim, only the map is in the other direction, sim V star, right? Now, this is a free algebra, so to define such map, we just need to know where generators go, and then we can consider this map. But it's not just any map. This should be a linear map, a linear representation. Then we land, along V star, we land into generators. So in fact, we land in OK tensor V star, sitting here. And after lowering index, we get exactly co-module structure. Okay. So one thing which I really need is that, like in the usual finite group representation theory, so this is a remark, representations of K is a monoidal category. If we have two representations, V1 and V2, then how to take their tensor product? We just take their tensor product in the outer sense first. This belongs to representations of K times K, obviously, because, and then we have the diagonal embedding, and then get V1 tensor V2 in representations of K, just restrict. So this is a monoidal category. So this tensor product is over the base field, over numbers. Since we have a monoidal category, we can talk about algebras in this category. So for me, an affine variety, an affine scheme with X, with K action, is the same as a commutative algebra OX in this monoidal category. So in other words, the map from OX, so OX should be a representation, and the multiplication map from OX tensor X to OX is a map of representations. And this gives a language to talk about, well, simple algebraic language to talk about equivalent quasi-coherent sheaves, which basically is my goal. So I don't want to give the more diagrammatic, if you wish, definition of equivalent sheaf, but just want to say that the definition K equivalent quasi-coherent sheaf on X, where X is an affine K scheme, is defined as an OX module M.
You don't want to view this as the category of finite representations of K?
It's not a finite dimensional representation. It's unions. It's unions.
So it is extending it by limits, right, in some sense?
Yeah.
Locally finite.
Local, yeah. But
So essentially, the algebra representations.
yes.
So you can think of finite representations and take sort of directly
Unions, yeah, direct limits, yes. So usually people talk about finite dimensional representations, but I don't like this because, for example, functions on the group itself, which is a natural representation, obviously, is not there. So then I want it to be there, and if I want to talk about equivalent sheaves, I'm bound to have infinite dimensional representations. So, okay. So here is a definition. An equivalent sheaf is just a module M in this category. So in other words, well, we have the usual module structure, but this map should be in rep K. So, well, just for the sake of completeness, equivalent definition. So M is, in the usual sense, a quasi-coherent sheaf on X. Now, equivariant structure is the following. We have two maps from K times X to X. They are usually denoted by D node and D1. So D node of Kx is X, and D1 of Kx is Kx. So then equivariant structure, so equivariance on M is an isomorphism alpha between two pullbacks. Well, satisfying cocycle condition, which I'm not stating right now. And an easy exercise is that in the affine picture, so when X is as affine, two definitions are actually equivalent. So, anyways, we have this category. So we have this category of quasi-coherent sheaves on X, equivariant with respect to K, and I'll be using later. So what I don't want to explain is operations on equivariant sheaves. I mean, there are usual push forward and pull back operations on quasi-coherent sheaves, and pull back can be directly upgraded to equivariant sheaves, and push forward requires more work, but it can be defined just as right adjoint to pull back. So, so I'll be using as a black box existence of pullbacks and push forwards in this picture with quasi-coherent sheaves. Well, we know that these functors are not exact. So in fact, remark from now on, in the previous situation, this notation means the derived category. So you can treat this as a black box. You can treat this, developing the standard machinery of resolutions and whatever, but I just don't want to use the long notation. I'll use the short notation. And whenever I'm using the words sheaf, it means a complex of sheaves up to quasi-isomorphism.
Will you be decorating your tensor products as L and stuff?
There'll be no tensor products.
F upper star will be L.
Yes. All functors are derived, and yeah. So, anyways, we just so now we come to geometric machine. So we take our G, which was my simple algebraic group, and for those who doesn't want to consider others, it's just SLN. And then we have the subgroup, which is B. And then the punchline, we consider the picture similar to the toy example. So we take G times G. Mod, well, I should put it like this. G mod B times G mod B. So these are actual quotients from the left and from the right. Now, over this, so it's known that, well, this is actually known under the name of flag variety, but one thing which is essential that this is an actual honest scheme algebraic variety, actually smooth algebraic variety, smooth projective algebraic variety. Over it sits, just as before, G times G mod diagonal action of B. And again, we have the multiplication map to just G. So I don't want to talk about stacks, so I'm using just this picture. So this is my geometric machine. And my algebraic device applied to this machine is simply taking equivariant sheaves. So one thing which I should remark here is that if well, a subgroup H in K, so for a subgroup H in fact, no, sorry. If K acts freely on X with a nice quotient Y, which is X quotient by K, so this means that X is a principal K bundle over Y, then the defined category of equivariant sheaves is equivalent to quasi-coherent sheaves on the quotient. So that's what you expect, and that's what you get. I don't want to explain this. Anyways, here is so what I want to define is the monoidal structure on quasi-coherent sheaves on G, which are bi-equivariant with respect to B. So if you recall my toy example, it's exactly the analog of this space F I was considering, only now it's a triangulated category. Well, in view of this observation, this is the same as quasi-coherent sheaves on G mod B, which are B equivariant, and this is the same as quasi-coherent sheaves on G mod B, again, which are B equivariant. But I am not allowed to take double quotient because there is no free action of B cross B. And, well, if you consider double quotient as a stack, then it's of course the same thing. However, so the monoidal structure is defined as follows. So suppose we have M1 and M2 in this category. Then what can we do? We can treat each of them on the corresponding factor, put the outer tensor product on the product, now this is a sheaf here, and the remaining equivariance makes it B equivariant from the left and B equivariant from the right. I'm pulling back. Now it sits here, and two equivariances remain. And then I'm pushing forward. So remember that all these operations are derived. So in fact, this operation is exact, so you don't need to take derived one, but this one is not. And this is my definition of convolution of M1 and M2. So lemma. gamma quasi-coherent sheaves on G with this convolution product is a monoidal triangulated category. And the unit object is, can you guess what is the unit object? It's just functions on B. So B sits inside G. So I just can consider functions on B as, and it is B bi-equivariant. You can translate it from the left and from the right. And the good thing about this algebra versus geometry is that, well, you take the structure sheaf on something which is bi-equivariant, it becomes a bi-equivariant sheaf. So now standard objects. In this category. So again, the idea is that we start from geometry. What is the standard bi-equivariant subset? Well, it's a subgroup containing B. Any subgroup containing B can be translated from the left and from the right. So it gives rise to a bi-equivariant sheaf. So, so let's take standard objects to be, so I'll denote them by DI, and they are just OPI. So PI, you remember, are these elementary, so minimal parabolic subgroups. So what can we say about these? We can say the following. So this is related to Bose-Samuelson varieties. So, so product of OPIs and Bose-Samuelson. So let's fix an element W in the while group, which is in our case is just the symmetric group. And it's a reduced expression. So the minimal length expression via simple reflections or via generators, so reduced expression. So people starting from de Mazur considered the following varieties. You take PI1 times so on times PIK. So notice that simple reflections and minimal parabolics are enumerated by simple roots. So to each simple reflection, we'll put in correspondence such P. Only now we take quotient in each pair. So let me put here PI2. So in here acts the diagonal copy of B, and we take quotient, and so on. And in the last place acts the diagonal copy of B. So there are K minus 1 copies. And since these are diagonal quotients, they respect pairwise products. So in particular, we can consider the product, the total product going to, so this variety, this quotient, is called Bose-Samuelson variety. Well, usually people take one additional quotient by B, but it's the same thing. So usually people, so B still acts from the right, so you can take quotient. Yeah, B's, so there are K minus 1 of them, and they act diagonal in each diagonal. In each pair, yeah, sorry. In this order. So this is a Bose-Samuelson. So what we are doing, we just taking the total product, it lands in G, but let's say where it lands. It lands into the product of subloops, pi1 times so on times pik. So in fact, this is known as a closure of a big Schubert cell, but I'm not actually using this. I'm just saying that this map, which I'll probably denote by mi1ik, then the theorem, probably in this form due to Klein, Partial, and Scott, and I hope there's two L's here. I'm not entirely sure. So this map of O in here and so push forward, and remember that this is the derived push forward. So first of all, this map is generically one-to-one, and second, so I won't need this, but what I'll need is that there's no higher direct images, and the direct image like this equals O on in here. Huh? Yes, yes, yes. Yeah, change. It's iterated. Yeah. Okay. Now, so I didn't explain how to calculate convolution I defined, but believe me that when I start calculating convolutions of OPIs, the intermediate step will be doing this. And as you see, the answer, no matter which order I took here, is the same. It's O on this thing, which, of course, and now I'm using that pi1ik is BWB bar. So it's the closure of the double coset.
So you don't like to use any other notation?
No.
He's not taking more B. It's still upstairs. It's still inside the group. It's still upstairs. It's still inside the group.
Yeah. So thus, well, right-hand side depends on W only, not on the reduced expression. Huh? Yes, the varieties will be different, and it's not about just some sheaves, it's about structure sheaves. So corollary, and again, I don't want to explain the details, but believe me, when you start doing this convolution, you'll see what's going on. So corollary, so for W in W, SI1, SIK, the convolution DI1 star so on star DIK depends on W only, not on the reduced expression. So this is first thing. Second, well, the theorem is actually more detailed. It explains what happens when the expression is non-reduced. I don't want to even write down this result, but I'll use this. So for any I, there exists a canonical map di to di, convolution di. And for any I, there exists a map from di to OB. So this is just restriction. So this is functions on pi, and this is functions on B, and this is my unit element in the monoidal structure. So making each di into a coalgebra in this monoidal category. And 3, in fact, so let me denote this map by delta I. So all delta i's are isomorphisms. So somehow I constructed a collection of objects which satisfy up to isomorphism a very recognizable set of relations. So remark. So 1 reads di's satisfy braid relations of the corresponding type up to isomorphism. I mean, if you think what braid relations mean, they exactly mean that whatever product you take, all such expressions will be, well, we live in categorical world, so isomorphic.
So that's essentially the underlying common products of the value over set.
Yeah. Now, so we constructed a monoidal category, and inside kind of an algebra. So you can take the span of these elements, and I'm not discussing whether they generate everything in some way or not. It's not important for me right now. They are just distinguished elements, and distinguished elements are kind of good. Up to isomorphism. Reads, so this 1, so that the fact that this product depends only up to isomorphism, of course. Reads that di's satisfy braid relations of the corresponding type up to isomorphism. Now, how we use this? Let X be G variety. So in particular, B acts on X. And we can consider, again, the derived category of quasi-coherent sheaves on X, which are B equivalent. We had the algebra geometric machine. Now there'll be a module geometric machine. The module machine looks like this. So we start from G times well, let me talk about categories. So I have G times X, and then I'm taking quasi-coherent sheaves here, which are equivalent with respect to B times B times B, right? So there's 2 copies of B acting on G, and there's 1 copy of B acting on X. Now I can do restriction of equivalence, which I still prefer to call delta star, and land in quasi-coherent sheaves on G times X, which are B times B delta equivalent. So I'm just restricting equivalence from this 2 copies of B to 1 copy of B here. And then there's action, which goes from G times X to X. And from this equivalence, I have only the remaining equivalence with respect to 1 copy of B. This is push forward. Now let M be in my monoidal category. and my n be G. So, what can I say? I can take M out of tensor product N. It will live here, restrict, and then push forward. And that's what I call M acting on N. So, proposition. This defines a monoidal action of this category on this category. So in particular, we have corollary. So we have functors. Have the functors, which I denote still by the letter di. So di of something is just convolution with di. Then, and they satisfy. G. Yes, I keep making this mistake. Thank you. So consider such functors. Well, each of them is a comonad. So we have canonical maps like this. And DIs satisfy braid relations up to isomorphism, up to a non-specified isomorphism. I'm not keeping track of isomorphism. So, for example, for SLN, we have DI. And now it's composition of functors. Di plus 1 Di is isomorphic to Di plus 1 Di plus 1. So such collection of data satisfy, so collection of common actually, since that was an isomorphism, all delta i's are isomorphisms, this map is an isomorphism. So comonad structure is given by, so it's kind of coprojector. So such data, so this is a remark, or maybe definition. A collection of DIs like this is called de Mazur descent data on a category. So I have constructed de Mazur descent data on any category like this. So this is a direct categorification, I won't write this down, of an, well, not so old result of Megumi Harada and a few others, which says that if we have, well, a space X with an action of G, then there is a way to compare T equivariant cohomology of X and G equivariant cohomology of X. Namely, you start from T equivariant cohomology, and that's the same as B equivalent cohomology because B contracts to T. And then one defines de Mazur operators. De Mazur operators now are one level down. It will be a collection of linear maps satisfying just braid relations because there's no place for isomorphism there, and satisfying that each of them equals their square. So we kind of lifted this one level up from the level of cohomology to the level of categories by this. Now I'm out of time, but let me finish by changing something just a bit, saying that the machinery stays the same and producing some other result. So, and I'm being extremely imprecise. Even this was not 100% precise, but so take the ring space. So instead of G with OG, right? So it's a ring space. Consider same topological space G, but change the ring of functions. We'll have here all differential forms on G, all algebraic differential forms on G. It's a DG algebra with zero differential. So this is a DG algebra with zero differential. So let's denote this space, discuss this reason. So then there is a theorem which is total analog of what we did before. We take quasi-coherent sheaves on LG, which are bi-equivalent with respect to LB and LB. So there are many algebras of differential forms involved, but so some of them play as the role of algebras, and when I write it like this, they play the role of coalgebras. Because what did I need to talk about coalgebras in the story? I was using pullbacks, but you can pull back not only functions but differential forms. So so this is a monoidal category, monoidal triangulated category. Now let's do the following. Let's repeat the story. Take OLPI. Well, it's just a fancy notation for omega pi as a module over omega g. Right? And since we have restriction, so we have the embedding of b into pi, we have canonical map from this to OB, OLB, which is the same as omega b. So it's a complex, two-term complex in this category, and let's take its cone and denote it by SI. Now, the theorem says, so this is like 1, and 2 SIs are invertible in the monoidal structure. And satisfy braid relations up to isomorphism. So these SIs, SI generate a braid group inside, well, So, huh? Yeah. So somehow the message is that I kept the geometric side of the picture. I changed the algebraic machine. Instead of O modules, now I consider omega modules. And the relation changed. So before I had this kind of degenerate Hecke algebra type relations. So these relations di squared equals di and whatever, and then braid relations. And now I have exact braid group relations. So in fact, any other incarnation of braid group I know in algebraic geometry comes from the action of this category. So
this can be interpreted in terms of the invariety and the corresponding Watson-Wilson objects there?
So the proof goes via known result of Bezrukavnikov and Risch, where they construct a certain braid group action. So I'm sure that it's equivalent to some calculation of push forwards of some omegas on Bott-Samuelson. I didn't do it. In particular, it would give an independent proof of Bezrukavnikov and Risch result.
Because the loop group category can have the invariety and have the corresponding.
Yeah. But this is not the actual loop group. It's kind of.
The analog.
Yeah. So maybe, you know what? Just to lose the rest of the audience, let me explain why this is the reasonable notion of a loop group. Yeah, so like before, if you make sense of them, I mean. So homotopy loop group kind of. So now this is algebraic topology. So the derived algebraic geometry turns out to be marriage between algebraic topology and usual algebraic geometry. So suppose we have X a topological space. And we want to define loops into X. So how should we do it? Well, we have paths into X. So these are unbased paths. So in fact, this is homotopy equivalent to X. I mean, you can fix, you choose one base point and then any path contracts to the base point. Okay, so then from this path space, there's a canonical map to X cross X, right? So starting point and end point. There's another map from X to X cross X, which is called diagonal. Now, what is a loop? A loop is a path which starts and ends at the same point. So it's fiber product of this and this over this. That's the loop space of X. So far, I didn't do anything fancy. But notice my remark that path space of X is kind of resolution of X. It's homotopy equivalent to X. Right? So then the loop space is X times resolution of X, so kind of X over X cross X, only in the derived sense. Now let's come back to algebraic geometry. So just remember this thing. Return to algebraic geometry. We take X times X over X times X. So X is a fine, so this is spec A. All right? So then what is this? In algebraic geometry, this is spec of A tensor over A tensor A, right? Only this tensor product, this fiber product should be derived. So this tensor product should be derived. Well, then I'm taking spec in quotes because I am just talking about some graded algebras instead of just algebras. Now, there's a theorem if A, so if X is smooth affine, then, well, tor I over A tensor A from A to A is omega I X, the ith differential forms. So in fact, the thing in question, so the thing we're taking spec of is just omega X. So there is a reason, and I mean, what I said is kind of analogy, and I didn't explain. Yeah. This is Hochschild, constant, Rosenberg. Yes, exactly. So now there is a world where all this can be made precise. And even without living in that world, one can make sense of all this. What should I add? So there was this conference in Kerala, and some of you were there. The language there of matrix factorizations is equivalent to this language. So this can be re-described in terms of certain matrix factorizations on the group G. And there'll be no fancy loops, no DG algebras, just usual matrix factorizations. It's the same result. And yeah, well, I can repeat in words that wherever, so if we have some variety X with G action, like before, one can construct a category on which braid group acts in the same way of push-pulls